Hello, welcome to our YouTube channel Civil and Structural Engineering Automation Ideas. I am Chandrakant Kulkarni. I have more than 39 years of experience in detail design and engineering. My expertise is in the detail engineering of residential structures, commercial structures, and infrastructures, including bridges, tall chimneys, storage silos, natural draft, induced draft cooling towers, industrial structures, oil and gas industry, metal and mining industry, and many more.
Hi, I am Nikhil Kulkarni. I have completed my master's in structural engineering and have been working as a structural engineer for past 14 years. My experience is in residential and commercial structures, industry structures, infrastructures like bridges, water treatment plants, sewage treatment plants, effluent treatment plants, and others. I have also worked in oil and gas industry and some blast resistant structures.
In the last video, we demonstrated how we automated analysis of foundation for multiple load combinations and checked the foundation adequacy for stability and bearing pressure with certain percentage contact limitation under service load conditions. As mentioned earlier, we calculated bearing pressure and percentage contact under various ultimate load combinations also. This video demonstrates how the foundation design is carried out using this ultimate pressure value. This video also demonstrates how the column design charts are generated and used here for design of particular size of section with certain percentage of steel. All the design calculations are carried out here are as per ACI 318 provision. Here, very simple approach for foundation design is used. It is as follow. Maximum bearing pressure under ultimate load combination is selected. The net ultimate bearing pressure is calculated after deducting soil overburden and foundation sulfate with appropriate load factor. Shear force per unit width at effective depth from face of pedestal is calculated by considering the above calculated net pressure as uniform load. Based on this shear force, one-way shear stress is calculated and compared with allowable shear stress based on concrete cylinder strength as per ACI 318 provisions. For calculating two-way shear stress, vertical loads and moments about both axes on pedestal at top of foundation is used and provision of ACI 318 are applied to calculate actual two-way shear stress. This value is compared with the limiting two-way shear stress based on concrete cylinder strength. Based on the maximum cantilever distance of footing slab from face of pedestal, the bending moment at face of pedestal is calculated for tension bottom case using this uniform net bearing pressure. With this moment, required area of reinforcement at bottom is calculated. Another approach is used here for calculating actual one-way shear stress and area of reinforcement at bottom. Here user defines net maximum pressure for which the footing must be designed. Same procedure is adopted for calculating shear stress and reinforcement. For design of columns, the beam end forces are picked from an external Excel sheet using Explorer. This is demonstrated while using the program. Once these values are populated in the design worksheet, the interaction ratio is generated for a particular section size with certain percentage steel. Here in general, Bressler load contour method is used with alpha as most of the time columns are tension control, meaning the actual load on column is less than 0.1 FCY multiplied by area of cross section as 1. If the section is compression control, actual load greater than 0.1 FCY into area of cross section, in that case reciprocal load method is used. This is demonstrated in the calculation as the calculations progress. Let us carry out the calculation using the program. Let us try to understand the results of this program once the program is complete.
So I think we can start the program.
Yeah. So again, we put
Let us fill the parameters. 2 meters is the footing width, 2.5 is the length, 0.5 is the thickness, 0.45 is the height, pedestal height. pedestal width 0.6 is the pedestal width. Zero finished. Top of concrete as 0.3. Founding level as minus 1.5. I think the program calculates these values, and this one will have to enter. This one will also be calculated. Hundred and sixty, and this is a yes, right? Okay, let us start. Reactions. Okay.
Okay. Now, since the program has completed the iteration, let's put cover to reinforcement as 40 mm. Then we put diameter of member 20 mm. Let's say. Okay, we say. Then let's say we design the footing for maximum pressure of 300 kilonewton per meter square, right? And we now select the file which is containing pedestal design loads, that is called pedestal design load. We have selected that file which will contain the beam end forces for the column design. Okay. Now it asks for the percentage steel. We say 1.2% steel, and we put say 4 bars at the top and bottom, and automatically two bars on each face. It will work. Yeah. Okay, the program has finished.
Yes. Now I think it's time we discuss the results of this program. So the results can broadly be divided into three major parts. As follows. So first one, we'll just think of analysis of foundation for biaxial bending under the service load combination. That covers the stability check against the sliding and overturning, percentage contact, and minimum bearing pressure. And analysis of foundation for biaxial bending under ultimate load combinations for calculating maximum bearing pressure. So let us go and see this.
Let's select the SLS combinations, one of the combination. Now we see here we are seeing a sort of a range which is having SLS reactions. Let's go to SLS reaction range.
Yes.
Now let's take case number say 1007 for that reason. Right now we have the support reactions which we have from the file is 53 kilonewton, 53 kilonewton as shear for FX, 242 kilonewton as vertical load, and 57 kilonewton as the lateral shear in Z direction. And of course there's a moments are zero because it is pin support. Now if you see the vertical load SL reaction at founding level, if you see that, if you click on that particular cell, you'll see the cells, certain cells are highlighted, which is adding to the vertical weight, the weight of the foundation and soil overburden plus the vertical load at the base plate reaction. So that covers the total vertical load at the founding level. Similarly, it calculates the moment about x-axis, which is nothing but the moment at base plate level, which is 0 of course because it is pin support, plus the moment force Fz and the lever arm. The lever arm here is difference between the top of concrete and founding level, which is 1.8 meter. So it automatically calculates. Same is the case for moment mx, as we can see here. Same is the case for mx, and then it calculates the pressures. Now, while we calculate the pressure, we see the pressure is 188 and 0. Now, if we try to analyze this foundation, let's go to our program called biaxial. Let's try to see what is how it is working here. Yeah, let's put now we have got 2 as the foundation width, 2.5 meter as the foundation length. What is the vertical load we have here in sheet 1 is we have 2.5. Let's go to the biaxial program. Now we have a vertical load of, particular for 1007 kg, 242. No, not 242 here.
In the sheet 1?
Yeah, sheet 1 399.297. Let's put that number there. Or we don't go that way. We go to biaxial program. Let's go to biaxial program, and then move. And then let's run this program here, and we'll populate the calculation. Say analysis is 1. Analysis 1. Enter. Then it asks for the foundation analysis rectangular 1. Yeah, and then foundation BF, which is 2 meters. Then 2.5 meters, right? And then vertical load, what is asking is vertical load is 399.297 kilonewtons. Then moment mx is 103.216. Moment mz is 95.5926. Yeah, let's see how the results are. Now let's see what numbers we are getting here. If we compare those results, we have a bearing pressure of 188.2295, right? And our result says 188. What is the number we get in sheet 1? 188.2292, almost. Yeah, it is the same result, right? And we have 4.36 as the factor of safety for sliding and overturning. Sliding and overturning factors are independent. If you click on the sheet there, you'll put the formulas there, which will work out sliding and overturning with appropriate axis. Then percentage contact we see is from the biaxial program, which is 96.23 or 36%, and then angle theta, which is angle which the neutral axis makes with the horizontal line, which is the angle is 55.3063. 55.3063. Angle theta. Sorry. 55 point. Yes. 55 point. 55. We have got a neutral axis of 2.6553.
2.6553.
If we see the biaxial program, 2.65.
Yes, 2.65.
So practically, earlier also we have validated this program biaxial when we use in our first video, which if you refer to first video, we validated our biaxial program for certain values. So it demonstrates that the program gives correct values. Now there could be argument that why we are doing so much of iteration and so many different load combination on so much rigorous calculation. The reason being, particularly for SLS condition, we need to check the percentage contact, which is quite important, and because of the loss of contact, there will be redistribution of pressures, and that will increase the pressure on the foundation, as well as it will reduce the loss of contact. When the loss of contact is reduced, there could be more rotation of the foundation, thereby increasing the rotation of the tip of the structure. So there are certain limitations for the percentage contact. We need to bear that in mind, so that the percentage contact as well as the bearing pressures are limited to certain limiting design requirement that will avoid excessive uh, distortion or the lateral deflections of the frames. So that is the whole purpose of doing this calculation.
So here essentially we are doing complete analysis for all the envelope of the load cases. So we are not leaving any load case, for we are not assuming, or we are not taking the maximum and minimum, or maximum positive and minimum maximum negative, or their combination. Rather we are taking each and every load case, and then we are calculating percentage contact, all the percentage contact, maximum pressures, minimum pressures, and all the related values for all the envelope of the loads. That is it.
That's correct. The one point we need to bear in mind is many a times we think we err on high side by considering maximum vertical load, maximum moment, absolute maximum moment in X and moment Z, but that is not true, because in some cases it is quite possible that the vertical load could be minimum and there are higher moments in the same load combination that will create high loss of contact as well as high pressures, because the area of the footing is reduced.
The concentration would be higher.
Yeah. So ideally, in this case, it is prudent to check that combination, and many a times we might slip that combination. So ideally, we need to consider,
especially for lateral load cases.
Lateral load cases. That's right. So particularly, this is more a robust way of checking the foundation stability and the pressures.
I think this is more applicable to tall structures, and this is also more applicable to slender structures with high, so say, wind loads or earthquake loads.
That's true. That's right.
Okay. So
now we move on to the foundation design.
Yes.
Design of foundation. Now this includes checking thicknesses for one-way shear, two-way shear, and calculation of top reinforcement, bottom reinforcement. Now another method, as per book Foundation Analysis and Design by Joseph Ball, also is demonstrated here. Here, effective contact length and effective contact width. So we refer to book by Joseph Bowles, wherein we can see here the effective length is calculated as L minus 2EX and width is calculated B dash equal to B minus 2F. So we use this approach in calculating the revised pressure redistribution, and we have used the same also in calculation of reinforcement and checking for the one-way shear. Then next part of this calculation is the interaction chart. But before we go to that, let us see what are the different things, different values which we have calculated in our foundation analysis and design. Let's scroll down. We have calculated the bearing pressure, gross bearing pressure under ultimate combinations, wherein the same way we have used the loss of contact and other parameters as we use for the SLS combinations. Same story, same parameters have been generated as per as above for as we calculated for SLS combinations. Then next thing we are seeing is we are calculating again same thing, bearing pressure, maximum bearing pressure, then minimum bearing pressure. If there's loss of contact, automatically it works out the neutral axis and percentage contact and angle at which the neutral axis is lying, as we have demonstrated in the program biaxial. So we have now generated the maximum pressures. As we can see, the maximum bearing pressure here is 242.24. We are using that pressure to calculate, do further calculation. Let's try to understand what those calculations are for the foundation design. Now we're saying, as we define 40 mm as a cover, and then 20 mm is the main diameter of bar, and then we have provided all the strength reduction factor as per ACI 318 provisions. Then we calculated the shear stress and one-way shear stress, limiting one-way shear stress, effective depth. Then based on that we calculated limiting shear capacity of the section, and we calculated also based on ACI 318 calculated the limiting two-way shear stress. We are calculating the shear capacity of the section. Then we calculated punching shear area calculation, punching shear calculation basically, and again we are using purely ACI 318 provisions. We carried out all these calculations based on ACI 318 provisions, and we generated the two-way shear stress based on that, which is 0.36 Newton per mm squared, as you can see here, maximum two-way shear stress, and we have limiting value of 1.35. So as you can see, the shear stress, two-way shear stress as well as one-way shear stress also is well within limit. Next thing we calculated is the reinforcement. Now before we calculate reinforcement, we calculated the moments for the tension bottom case and tension top case. If we click on the that particular case, we see the maximum pressure is calculated, which is net pressure after deducting the soil overburden and the self-weight of the foundation with appropriate load factor. We calculated that net bearing pressure, which is in here is Scott, is how much is 199.546 Newton kilonewton per meter squared, and we have maximum pressure for top steel design, which is purely soil overburden plus self-weight foundation with appropriate factor, which is 42.7. So we use that loading and calculated the with cantilever lever arm of 950 mm. We calculated bending moment as a cantilever, which is 90 kilonewton meter and 19 kilometer meter for bottom and top respectively. Then we design the steel for that. As we can see further down, we have a reinforcement requirement of 489 mm squared and with a neutral axis of 10 mm, and let us check the case for user defined pressure of 300 kilonewton per meter squared. Let's see what is happening there. 300 kilonewton per meter squared pressure. So 300 kilonewton per meter squared is the pressure. Now we have calculated one-way shear stress as 0.33 Newton per mm square. Then maximum cantilever moment is 135 kilonewton meter. Now if you see, the area requirement is 739.776 mm square, and for that neutral axis is 15.968 with total force which is equated to 0, as we can see, which is 1.04 10 to the power of minus 13, which is negligible. So practically it iterates these values and satisfies the equilibrium condition of zero force and moment, which is 135.375, and for that moment it calculates this reinforcement and area of steel. So same calculations are repeated here for ball's pressure, which is 173.473. We have calculated net pressure of 130 kilonewton per meter squared. Then we have calculated one-way shear stress, which is 0.145. Maximum cantilever moment is 59 kilonewton meter, and reinforcement is 319 mm squared. And we see that again the compatibility of forces and moment is achieved by providing that steel and a certain neutral axis, which is 6.89 mm. So this is all about foundation design. Let us quickly move down to the reinforcement design for the column. Now we have a column size of 450 by 600 mm, which is already defined initially. and we have picked up those values of the column design from pedestal design Excel sheet, and here it checks the interaction ratio. It does check interaction ratio for various cases. As I said earlier, it checks based on Bressler load control method. If the actual load is less than 0.1 fcy into area of section, then it will check the ratios of moment to moment. If the actual load is more than 0.1 fcy into area of cross section, then it will check the load capacity for individual moment, and then based on the reciprocal load method, it will work out the interaction ratio. The same thing has been provided here. The interaction ratios are generated, as you can see on the right of the sheet. The interaction ratios are generated, and these ratios, from these ratios, the interpolation has been carried out for various values of the loads and corresponding moments. So axial load, certain axial load, for example, if we take a load of 2000 kilonewton, let's take a load of 2000 kilonewton here. Now here we have a moment, major axis moment as 200 kilonewton meter. If we see that MUX chart where we find 200 kilonewton meter moment, let's see here on this chart where we have 200 kilonewton meter moment or 2000 kilonewton load, for that because load is predominant. 2000 kilonewton load, we have approximately 531, 500, almost say 510, 20 kilonewton roughly load, 520 kilonewton load, and we have a moment 520 kilonewton meter moment, sorry, and we have a moment of 200. So 200 divided by 520, 2000. No, I'm talking about the moments. Okay. 200 divided by 520 comes to almost 0.44. If we calculate that, 0.3846. Let's see how much is the number there. What we have got there. 0.446. Because in this case we are going the other way around. Rather, we need to see for 2000 kilonewton load, or rather for 200 kilonewton meter moment, what is the load. Let's see the other way around. 200 kilonewton moment. Now where is the 200 kilonewton meter moment? Here we have 222 and 172. So I have a limiting load of 4418.963. If I calculate the ratio of load to load, 2000 divided by 4481.96. So what is the ratio we have is 0.446. We are getting the same ratio here. So this is the reciprocal load method we are using here. As you can see, that ratio is 0.446. So there are two different methods. One is the reciprocal load method which we are using here, and another is the load control, wherein we are using for particular load what is the moment capacity. So in this case we have demonstrated this number. Let's quickly check what is the maximum value we have here for the interaction, which is highlighted in green. Yeah, here we have a moment of a load of 255 kilonewton, right? Load of 255 kilonewton and a moment of 280.95 kilonewton. Now for the 255 kilonewton load, let's check what is the limiting load. 255 kilonewton meter moment, what is the limiting load? We have a limiting load of 255 kilonewton meter moment up 267 and 74. So we have no, that is a negative piece. No, wait, 255 kilonewton load. What is the moment we have is
255 is the moment, and
vertical load is how much? Vertical load is 250. I'm sorry. Vertical load is 250. Well, let's go to for that 255 kilonewton. What is the moment capacity? Let's see. Let's see for the major axis only. 255 kilonewton moment. We have a load capacity of almost 400, 4,400. No, something is not right. Let's see again the value. Sorry, we have a value of 255 kilonewton as a load, and no, this is actual force. 255 as per stat. 255 kilonewton is the actual compression.
Actual compression.
Compression. 255 is a compression,
And
and moment is 280. So for 255 kilonewton load, let's see. Let's see. 255 kilonewton. No, now here we have a 255 between say 385 and so 351 and 26. So it could be something to the tune of maybe 400 and maybe 400 and 410 420 kilonewton load. Now we have a load of 255. So 400 255 divided by 410 or 20 roughly. I'm saying. 0.62. So that is the number which we are getting approximately. I am saying approximately, but this program is working out more rigorously, and we are getting a number of how much? 0.63. Seems to be in close agreement with what we have there. That's fine. So ideally, this is what our program uh, does the calculation for the column interaction charts. I believe this is what we want to show this in this video.
Okay, I think yes, this clearly demonstrates that a lot of times we just take the maximum movement, maximum load, and we just design the foundation for maximum values of the loads or their permutation combination maximum and minimum, but that should not be the case. That is not the right way to do the design of foundations. We need to consider a lot of other things other than just the maximum values. So I think this program nicely demonstrates the lacuna that is prevailing in the current industry standards. So I hope this program will help you guys to understand that lacuna and fill it up. Yeah.
Thank you very much for your time.